wanted to introduce tonight's guest speaker. As I'd mentioned, we had a lot of wonderful discussion about this, and we are just really fortunate to have Dr. Hand join us tonight. For those of you who have read his book, you obviously have a keen interest in listening to the talk tonight. For those who don't know Dr. Hand, he's a planetary scientist and astrobiologist at NASA's Jet Propulsion Laboratory, where he directs the Ocean Worlds Lab. His research focuses on the search for life in the solar system, with an emphasis on Jupiter's moon Europa. He's helping lead NASA's Europa Lander mission concept, and from 2011 to 2016, he served as Deputy Chief Scientist for Solar System Exploration at JPL. His fieldwork has brought him from the Arctic to Antarctica and the depths of Earth's oceans. His book, Alien Oceans, was recently published by Princeton University Press, and it's my pleasure to welcome Dr. Hand to the HAS meeting this Friday. Dr. Hand, thank you very much for joining us.
Thanks, Joe, and thanks, Don, for all the help setting this up. And it's great to be here and see a lot of faces out there. Obviously, we all wish that we could be gathered together, either in an auditorium or better yet, outside under the night sky with some nice telescopes. But thank you for coming this evening, and thank you for reading my book. It came out April 7th of 2020, which, as you can imagine, after about a decade of working on it and writing it, to have such a passion project come out right at the start of a pandemic was less than ideal. But of course, there were bigger picture problems, and so I'm still thrilled that folks are finding it and reading it and enjoying it. Okay, so let's see. I'm going to share my screen. We tested this out earlier, and hopefully it'll all go as planned.
We're seeing it come up. And I was just going to let everybody know that if you have any questions for Dr. Hand throughout the course of the conversation, use the chat function that we have within Zoom itself. Ask your questions there. We'll queue those up for the end of the meeting. And Dr. Hand has been gracious enough to answer. He said he would answer some of those questions when we get to the end. So take it away, Dr. Hand.
Absolutely, and please, I appreciate the respect of PhD and all of that, but just call me Kevin.
All right, Kevin, thank you.
We one astronomer to another, so for all of you out there. Okay, well, so tonight, as you know, I'm going to be speaking about alien oceans and the search for life in the depths of space. And this, of course, is in abbreviated form what I cover in my book. It looks like a little, that's interesting. It's okay, well, I'm holding up the book there, and in the background, you can see a lander on the surface of Europa. I'll talk a bit about our latest development of that mission concept. But so at the heart of my work, at the heart of this book, is the fact that we live in this really incredible time where, for the first time in the history of humanity, we can ask this incredibly profound yet unanswered question: are we alone in the universe? Is there life beyond Earth? And while it is a question that covers quite an incredible range of possibilities, just to set the stage at the appropriate level and set your expectations at the appropriate level, tonight I will not be talking about UFOs, alien abductions, ET, or other furry little creatures from purported distant planets. When I talk about the search for life beyond Earth, and for that matter, when NASA engages in the search for life beyond Earth, for the most part, we're talking about the search for even the tiniest of microbes, a single-celled creature that in and of itself, despite its small size, would revolutionize our understanding of biology. And when we think about the story of the search for life beyond Earth, it really is the story of this beautiful blue marble reaching out into our solar system and beyond. And this diagram, this beautiful diagram put together by National Geographic, shows a line. That's my dog sneezing in the background. I don't know if you can hear. So each of these lines is a robotic spacecraft that has gone out to a different world and beyond. You see many lines to the moon, many to Venus and Mars, a few to the sun and Mercury. but there are just a few lines that extend beyond the asteroid belt. And these lines represent spacecraft with names like Pioneer, Voyager, Galileo, Cassini, more recently Juno and New Horizons. And one of the most exciting discoveries that's been made by these spacecraft over the past several decades is that we now have good reason to predict that oceans exist beyond Earth. This is a portrait of what I like to consider to be the ocean worlds of our solar system. At the center, of course, is the Earth. And around the Earth, I've placed 6 moons of the outer solar system: Europa, Ganymede, and Callisto, 3 moons of Jupiter, Titan and Enceladus, 2 moons of Saturn. And I've even got Neptune's curious moon, Triton, here. These worlds are covered in ice, but beneath their icy shells, we have good reason to predict that vast, potentially global liquid water oceans exist. They are there today, and in some cases, we think that these oceans have persisted for much of the history of our solar system. And these worlds are really changing the way we think about habitability and what it might take for a world to harbor life. As many of you appreciate, in the early days of astronomy and planetary science, the kind of planetary context for a habitable world was founded on the distance from your parent star. And we kind of had this Goldilocks scenario of Venus, Earth, and Mars, where Venus was too close to the sun, too hot, boiled off any water that it once had. Mars is too far away. The water that it once had froze out and got lost to space. Both those situations are much more complex than I'm going to get into this evening. But then the Earth at 1 astronomical unit is at just the right distance so as to maintain and sustain a liquid water ocean in contact with a thick atmosphere. And that ocean is the oasis of life on Earth. And that was sort of our prototype for habitable planets. Well, that's an old Goldilocks, and there's a new Goldilocks in town. It's one wherein the energy for maintaining and sustaining liquid water oceans comes not from your parent star, but rather from the tidal tug and pull of a world as it goes around a giant planet primary. And there's no better demonstration of the sheer power of tidal energy than Jupiter's innermost large moon, Io. Now, Io, of course, does not have an ocean. It has long since lost any water that it may have had early on. But Io, as can be seen in that inset, is the most volcanically active body in our solar system, more volcanically active than even the Earth. And in that inset, you can see near the North Pole of Io, an umbrella-like feature, which is a volcanic eruption ejecting material out into space, which then comes back down onto Io. And so Io demonstrates the extraordinary power of tidal energy dissipation. And the Galilean satellites, Io, Europa, Ganymede, and Callisto, really provide an interesting new Goldilocks for these ocean worlds, these worlds that are covered in ice, yet harbor liquid water oceans maintained through tidal energy dissipation. Callisto, the furthest out of Jupiter's large moons, Callisto does not have much in the way of tidal energy. It probably does have an ocean. There's a lot of work still to be done on Callisto. If it does have an ocean, there may be a whiff of tidal energy coupled with radiogenic decay of heavier elements. And Callisto is a beautiful world in its own right, but from an astrobiological standpoint, from a search for life standpoint, Callisto's ocean is trapped beneath a very thick and old ice shell, as evidenced by all those pockmarks that you see on Callisto's icy surface. Io, as I mentioned, has too much energy. Io is kind of like the Venus version of a world in this new Goldilocks. Callisto, you might consider Mars-like. And in the middle, we've got Europa and Ganymede. And Europa in particular may reside in this sweet spot where it's got just enough tidal energy dissipation so as to maintain and sustain that liquid water ocean, an ocean that is perhaps 60 miles in depth, 100 kilometers in depth, beneath a relatively thin ice shell. And when I say relatively thin, I mean of order 10 kilometers. I happen to think that globally averaged, it's thinner than 10 kilometers. Many of my colleagues argue that it's quite a bit thicker. This is one of the key questions that we'll answer with the upcoming Europa Clipper mission, and possibly even with the extended mission of the Juno spacecraft. So Europa is this kind of new Goldilocks zone for these ocean worlds, these ice-covered oceans beyond the Earth. And of course, as I mentioned earlier, the reason why we're so excited about these alien oceans beyond Earth is because if we have learned anything from life on Earth, it's that where you find the liquid water, you generally find life. Whether it's in our ocean depths, in hydrothermal vents, as shown at the left, or in the dry valleys of Antarctica, as shown at the bottom right, or in hot springs in the Rift Valley, whether it's life in extreme environments or life of extreme lifestyles, all life on Earth depends on liquid water. Now, hopefully, were we in an auditorium, I would at least get a little bit of a laugh out of that. But that's one of the, I can see Joe laughing a little bit there. But I like to show this collage for another reason, which is that for all of the diversity of life on Earth, from the most extreme of microbe at a hydrothermal vent to Mick and Keith as extreme rock stars, not only is all life on Earth dependent on liquid water and carbon and a number of other aspects that connect us all, but in addition to all that, all life on Earth runs on the same biochemistry. We are all connected by DNA, RNA, proteins, and ATP. And so when we think about the tree of life on Earth, we are all connected, and we've come quite an incredible way in the past few decades. Over that same time period when we were just beginning to explore the solar system, biology has begun to undertake quite a remarkable revolution by merit of genetics and understanding molecular biology. This was the great tree of life as depicted in 1955. Fast forward to just a couple of years ago. Apologies, let me take a sip of water here. Fast forward to 2016, and now this is our tree of life on Earth, dominated by microbes. All of those three major branches there and the various branches that you see primarily correspond to microbes. Mick and Keith and us and just about all the other things we're way down here on a tiny branch of the eukaryotes. And so part of what's exciting about exploring these alien oceans beyond Earth is that these are locales where we can truly go today and search for extant life that's alive today. And if it is there, not only will we answer that question of are we alone in the universe, is there life beyond Earth, we can also begin to understand its biochemistry and unravel whether or not there are various contingencies and convergences associated with different modalities for the origin of life itself. Would life on Europa run off of DNA, RNA, and proteins, or is there some other game in town? And this aspect is really critical of discovering extant life. I'm part of the Mars 2020 mission. I love Mars. I hope that perseverance and curiosity go over a hill and discover microbial stromatolites in the rocks on Mars. But the ancient rocks on Mars are not really going to permit us to analyze in detail whatever biochemistry may have underpinned past life on Mars. And that is because those large biomolecules do not last long in the rock record. We know that from our old rocks on Earth. we don't find DNA in billion-year-old rocks on Earth. But with these alien oceans, these are places where life could be alive today, extant life. Certainly, we're not going to discover alive on the surface of these worlds, but someday we could actually get in there and examine the biochemistry of that life and figure out whether or not that life represents a second independent origin and what that tree of life is founded on biochemically. So that gives you much of the big picture motivation. I'm curious whether or not biology works beyond Earth. We know it works here on Earth, but biology is the last of the major sciences that we have yet to extend beyond our home planet. We know that physics, geology, and chemistry all work, but we have not yet made that leap with biology. So how do we know these alien oceans exist? Well, it begins with, of course, ground-based telescopes initially, but then extends to these spacecraft that have flown by these worlds. Shown up left is the Cassini spacecraft in the spacecraft assembly facility at JPL. And at the upper right is the Galileo spacecraft, which, as many of you appreciate, was launched from the space shuttle. That's why we have a picture like this. This is before the rocket fired to take it on its trajectory that would actually head in towards Venus before getting slingshotted back out towards Jupiter. And then, of course, to give appropriate credit where credit's due, these spacecraft would be useless if we didn't have the ear on the ground, the Deep Space Network, one of the dishes of which is shown at bottom right. And from these spacecraft, we of course have beautiful images like this of Saturn. And tonight I'm just going to go into a bit of detail on Enceladus and Europa. And then I'll take you back to Earth and talk about some of the exploration I've done on Earth that has helped inform our understanding and search for life beyond Earth. So Enceladus is a small moon. It's just about 500 kilometers or 300 miles in diameter. And it's a moon that tells a various curious story with its icy shell. As you can see in this image, the northern hemisphere of Enceladus is pockmarked with craters. And to a planetary scientist, an abundance of craters is the hallmark of an old surface. And if you just take the cratering age at face value, estimates are that the northern hemisphere of Enceladus is somewhere in the range of about 3 to 3.5 billion years old. But to the south, we of course see very few craters, implying a very young surface. And along with that, towards the south, we see these fractures, these tiger stripes, as they've been come to be called. And when the Cassini spacecraft took this image, the team decided that these fractures needed a closer look. And on that subsequent flyby, the Cassini spacecraft captured this image. And here again, were we all in an auditorium, hopefully I would be hearing some oohs and some ahs. This is arguably one of the most stunning pictures ever collected by a spacecraft to date. What you're looking at here, of course, is an ocean erupting out into space. Those tiger stripes, those fractures that you saw in the previous image, we have good reason to predict, based on some of the data I'll share with you, those fractures connect to a subsurface ocean, which initially was thought to be just a south polar ocean, but now, based on some of the wander of the ice shell itself, we think it is a global ocean within Enceladus. And the plumes of material here are in fact oceanic material being ejected out into space. Looking down at Enceladus' surface, these plumes, as magnificent as they are, it's not quite like looking at a snowmaking machine at a ski area. They're quite diffuse, but in this image in particular, you can see sort of in the bottom middle region, there's a dark hole here. Joe, can you see my cursor?
We can, yes.
So right where that cursor is may well be the home of one of those jets. And you can see around the perimeter there, the surface is perhaps covered with Enceladian snow that has covered up some of the fractures that are in the more distant regions. And so while you cannot directly see the plumes unless the lighting conditions are just right, so you get the scattering off the particles, you can infer the plumes from these downward facing images just through the softening of the surface. So how do we actually think we know that these plumes connect to a subsurface ocean? And here is where, so I was not a scientist on the Cassini mission. I was working on Galileo data at the time and trying to unravel some of the mysteries of Europa. But I was staying abreast of Enceladus's data, and early on, I'll admit that I was very skeptical as to what Enceladus was telling us. I thought that Enceladus might be a glorified comet. We of course see jets of material coming out of comets. Maybe Enceladus has got some sort of comet-like jet behavior occurring that has nothing to do with a subsurface ocean. Because keep in mind, here again, like the Enceladus is such a tiny world, and the tidal energy predictions were that Enceladus does have some significant tidal energy dissipation, but it was not as obvious as the case of, say, Europa. So I went in skeptical, but sure enough, year after year, the Cassini data mounted increasingly compelling evidence for a subsurface liquid water ocean. And let me just go through a little bit of that, at least some of the chemical data quickly here. So first up was the INMS, the ion and neutral mass spectrometer instrument on Cassini. It collected this early data, which indicated water vapor, methane, some interesting simple organics, carbon dioxide, and some cracking of perhaps more complex organics. The mass spectrometer, the INMS, did not go up to high enough masses to really figure out much of the complexity of those organics. But nevertheless, that spectrum at the upper left was quite compelling, but did not rule out the cometary hypothesis. And that is because, of course, comets also have jets of water that contain organics. Next up was the cosmic dust analyzer, and the results from the CDA, as it's known, are shown in the middle, and then the diagram at the right, and then also at the bottom right there. And the cosmic dust analyzer found salts in the E-ring grains. The E-ring is derived from the plumes, and it eventually found salts in the plume material itself. And geochemically, it is darn hard to have a plume rich in salts and these other materials without having some sort of water-rock interaction. And so when the Cassini spacecraft found salts in the plume material, that is when some of the more skeptical members of the science community, like myself, began to turn the corner towards thinking that Enceladus does in fact have a liquid water ocean. And then following on that, the INMS, again, that spectrometer that show spectra of in the upper left there, towards the end of the Cassini mission, the INMS found hydrogen in the plume. And that not only indicated some geochemical activity and was also consistent with the liquid water ocean, but that data for hydrogen also pointed towards hydrothermal activity within Enceladus's ocean. And by hydrothermal activity, I mean this kind of hydrothermal activity. This is a picture that I took during a dive I made at the bottom of our own ocean. And I think, as many of you appreciate, in the depths of our own ocean, cut off from sunlight, are these hot springs that drive chemosynthetically supported ecosystems contrasting that with photosynthetically supported ecosystems. And these, the rich chemistry of the hydrothermal vents feeds chemosynthetic microbes. Those microbes then allow more complex life to exist. There are a bunch of caveats to that, including oxygen dissolved in the ocean water that's derived from photosynthesis. But nevertheless, the hydrogen at Enceladus pointed towards hydrogen produced through hydrothermal geochemistry within Enceladus. And so our current model, pardon me, let me give my dog a little love. She I'm whimpering back there. Got a nice little treat now. And so this is our current conception for Enceladus. Those plumes at the South Pole. We now do think that the ocean is global, and the ice shell may be anywhere from a few kilometers near the South Polar Terrain to as much as several tens of kilometers elsewhere. And the ocean itself may well be tens of kilometers in thickness. That's kind of the best available knowledge and modeling that is consistent with the Cassini data. And until we get a spacecraft back out there, we just will not have any further data. And hopefully we can, in the coming decade, prioritize a mission to get out to Enceladus. So let's move on to Europa. Europa is a much larger moon than Enceladus. Europa is about 3,000 kilometers in diameter. That's comparable to the size of our own moon, shown here relative to the Earth and to Jupiter. And sorry, I didn't expect to be losing my voice. This is what I get for being on telecons all week. So the Jupiter, as you know, or likely know, is some 318 times as massive as the Earth. And so, of course, given our experience with tides here on Earth, just imagine what it would be like to be on Europa experiencing that force of Jupiter as Europa goes around its slightly elliptical orbit. Some models predict that if you could stand on Europa, which you would not want to do, too cold, radiation is too intense, but if you could, you would rise and fall by nearly 100 feet with each 3.5 day diurnal cycle on Europa. Now, I'm not going to go through how we think we know there's an ocean within Europa. I like to break it into 3 easy pieces. In the interest of time, I'm just going to say, if you read the book, you know the 3 easy pieces. If you haven't read the book, I encourage you to read it. There's a lot of fun history on spectroscopy in the chapter on the first easy piece. There's a lot of interesting history about the Galileo mission in the second 2 chapters about the second and third easy pieces. And if you've got questions on those, of course, we can come to those during the Q&A period. And so through that data that we have from the Galileo spacecraft, which includes the spectroscopy, the gravity data, the magnetometry, our current cross-section for Europa is that it's got an iron core that's iron or iron sulfur core. That core is overlain by a rocky silicate mantle. And then above that is this ocean that's roughly 60 miles in depth. And above that is this ice shell. And in this little video, the coloration shown is meant to indicate that whether through direct fracturing and resurfacing or by warmer ice rising up through what we call diapirs, the ice shell of Europa is recycled on a very short geologic timescale. There are very, very few craters on Europa. And so when you do the crater count math, Europa's ice shell on average is in the range of about 10 to 100 million years old. And so we think that Europa's ice shell provides a very good window into the ocean below. And here's that cross-section just in sort of cartoon form. Just a few pictures of Europa to give you a sense of how beautiful and bizarre its icy surface is. Uh, One interesting kind of geologic feature that's quite a bit different from anything that we see on Enceladus is that Europa has these chaos features, these rafts of ice that if you're on Earth, you would say that's an ice sheet or glacier breaking up and kind of moving off into the Arctic Ocean or Antarctic, but it's far too cold. The surface temperature of Europa is minus 280 degrees Fahrenheit, roughly 100 Kelvin. And so, sounds like somebody's open line there. I don't know if it's possible to mute folks, Joe, but so
Let me take a look there.
we don't see this kind of geologic ice feature on Enceladus, and we do think that this kind of feature, these chaos features, are perhaps an example of oceanic material coming directly to the surface, or in a thicker ice shell model, warmer ice punching through a brittle ice shell and perhaps convecting material up to that surface. Here are some of those bizarre fractures and ridges and some little freckle-like features on Europa's surface. And another aspect of Europa that's particularly curious is that Europa's fractures are colored in this red, brown, and sometimes yellowish material. And this is something that has caused myself and my fellow scientists to scratch our heads for quite a long time about what that reddish brown yellow material implies for the subsurface ocean. And coming out of the Galileo mission, the spectrometer on Galileo indicated that this material might be indicative of magnesium sulfate, possibly a salt from the ocean below. But there was a lot of debate about that. I won't get into too much detail on that, but suffice to say, many of us, as much as we wanted to believe that the reddish brown material was in fact salt from the ocean, just didn't feel like the spectra of Galileo's near-infrared mapping spectrometer were sufficient to rule out the alternative hypothesis of the reddish brown material being primarily radiation processed sulfur delivered from the volcanism of Io. So this debate went on for quite some time. And then a few years ago, my colleague Bob Carlson and I, who happened to be PI on the Galileo near-infrared mapping spectrometer, and he was one of the adherents against the salt hypothesis for the interpretation of the available spectra, which was quite wonderful because it would have served him perfectly well to go with the juicier, more favorable, exciting hypothesis of endogenous salts. But Bob rejected that and said, well, so we teamed up and we decided to do some experiments to see whether or not we could figure out whether or not Europa's surface radiation environment might be able to tell us a thing or two about the nature of any salts that might occur on the surface. And so just a bit of background there, Jupiter's magnetic field sweeps over Europa and bombards Europa's ice with energetic electrons, ions, protons, etc. It's a very harsh environment for a spacecraft, but the radiation may well be advantageous for figuring out what the surface is made of, and also potentially providing some chemistry that life below could use. So here's a picture of our lab at JPL, the Ocean Worlds lab. One of the chambers that we've got there, I like to refer to as Europa in a can. Basically, we can get down to Europa temperatures and pressures, and we can turn on an electron gun and irradiate any material that we put in the chamber. And so one of the things we did is we took table salts, reagent grade table salt, sodium chloride, and put it in the chamber. Now, as you know from your own experience, salt is white, and spectroscopically, it's also quite flat. But after putting it in the chamber and irradiating it under conditions similar to Europa's surface, that salt turned this very distinct reddish brown yellow color. And when I first pulled this sample out of the chamber, my jaw dropped because immediately I said, without even having to look at spectra, I said, this is very much what at least some regions of Europa's surface look like. And so in the years since we did that experiment, we looked back at the Galileo data, we looked at other ground-based data, and most recently, we collected some new spectra with the Hubble Space Telescope. And this was a project led by Samantha Trumbo, a brilliant grad student at Caltech. And Sam got us time on the HST and collected these spectra shown in black here of Europa's surface. And shown in red here, if you can see it, is my spectrum from the lab. And sure enough, this particular discoloration feature that we saw in irradiated sodium chloride was found in this region on Europa. And so we think irradiated sodium chloride is sort of this smoking gun for oceanic salts on Europa's surface. I like to think of it kind of like invisible ink. It's not until you irradiate the sodium chloride that it becomes spectroscopically and visibly observable. So that was a great sort of mystery that we solved recently, and which I think a lot of our colleagues have converged on and agree with now. This mosaic is one of the highest resolution images that we have of Europa's surface, 6 meters per pixel at the best resolution. This is a grayscale image. If this were in color, it might be sort of yellow, brown, red. That cliff here at the end is perhaps a few hundred feet in height. And I love to think that perhaps the talus, the icy blocks that have fallen off that cliff, may well have evidence of microbes, of European krill, possibly even more complex creatures. But we just won't know until we get back out there. And so when are we going to get back out there? Well, in the near term, the Juno spacecraft will be making some close flybys later on this year and in the years to come. And after that, hopefully in 2024, the Europa Clipper mission shown at left will get to the launch pad. It was just recently announced that it will fly on a Falcon Heavy. And then at right is the European Space Agency's JUICE mission, which will hopefully get out to Jupiter around the same time. Both of these missions could well be in orbit around Jupiter in the late 2020s, early 2030s. Coupled with that, we've got the Dragonfly mission. I'm a scientist on this mission. I don't have time tonight to go into detail on Titan, but Titan is one of my favorite alien ocean worlds. And the Dragonfly mission will parachute down in the mid-2030s. Dragonfly is currently scheduled for launch in 2027. And it will use its rotorcraft to investigate the mid-latitude region of Titan. And it will be able to make several hops around Titan over the course of many years. A truly remarkable mission that's just going to be so exciting once it gets out there. And lastly, brief in terms of hopefully the somewhat near term, is a lander on the surface of Europa. Now, this is not an approved mission. We're still in what's called the pre-phase A stage. And as Joe mentioned, I'm the pre-project scientist for this mission. It's a bit of a Sisyphean task. I've been trying to get a lander to the surface of Europa now for over 15 years. I've worked very hard on Clipper. I'm a scientist on that mission, and it's a beautiful mission. But I sure hope we can follow up Clipper in close cadence with a mission that goes to the surface and saws, drills, excavates down into that surface material to directly understand any indicators of habitability and to search for potential biosignatures. This mission, I won't go into great detail on, but we've held a number of workshops and some of that material is online. I think if you go to europa.jpl.nasa.gov, you'll find some links to that. but I'll just share with you a little bit. I'm going to kind of click through this. The mission, so this animation is all based on our detailed CAD models that then allow for this beautiful animation to be constructed. The lander would come out of a solar-powered carrier stage. Then we would get to Europa's surface by using the sky crane. It's actually a bit of a lighter spacecraft than either Perseverance or Curiosity on Mars. The lander itself is in the range of about 500 kgs. And when Perseverance landed on Mars just a few months ago, it utilized terrain relative navigation to get to just the right safe spot on Mars. We're going to be using that same set of algorithms and processing to navigate the surface of Europa, which, despite the Clipper imagery, will still be unknown at sort of the lander scale. And that's where the brilliance of the engineers at NASA and within JPL, et cetera, are just, it's just so remarkable. The TRN, terrain relative navigation, is such an enabling capability for exploring these far and distant worlds. So once we sit down on the surface, the lander will use, in this animation, a bi-blade excavation system to get beneath the radiation process surface material. It'll go to a minimum of about 10 centimeters depth. It could go as long as the arm is, but our requirement is at least 10 centimeters. And then it'll scoop up a sample and deliver that sample to the body of the lander, where it will be ingested and then distributed to a set of instruments that will analyze the chemistry and look for any biosignatures. And in my sort of dream of dreams, we discover signs of life and change our understanding of our place in the universe forever and ever. So just looking at the clock, I want to quickly go through a couple of highlights about exploration here on Earth. Joe, I'll try and finish in the next like 10 minutes. Does that sound good?
No, absolutely. Take as much time as you need.
Okay, I know we want to leave some Q&A time, right?
Sure.
Great, so I'll go through this quickly, but we can come back to it. Part of what I love about the search for life in these ocean worlds is that it presents an opportunity for a win-win, both technologically and scientifically, for advancing our capabilities for exploring our own ocean and our own cryosphere. And in so doing, enhancing our capability to better understand planet Earth that's got the ocean we know and love and need to take care of. And so shown here at top is the Europa Clipper mission, and then the lander. And as we eventually want to get into the ice shell and beneath that ice shell and into the ocean directly, we're going to need robotic capabilities that are tested out in our own ocean that can conduct comparable types of exploration in these far and distant ocean worlds. And so we'll travel just to two places this evening. The first is to Casey Station in Antarctica. I had the opportunity to travel with our team down there towards the end of 2019. And this was not too long before COVID broke out. And it seems like a lifetime ago. The Australians invited us to go down there to test out our robotic vehicle that we call the Buoyant Rover for under ice exploration. And towards the end of our time there, they even added a sign to their signpost here. I don't know if you can see the Europa sign at the bottom there. We had some debate that technically that sign is not pointing towards Europa. That's not quite the right angle, but we figured for good measure, just having it point to space was probably got the gist across. So here's our Buoyant Rover for under ice exploration. Penguin approved, and and Antarctic tested. The rationale for an under ice rover is that the ice water interface is a very interesting and chemically rich boundary between liquid water and, of course, ice above. And on Earth, there's a tremendous amount of biology happening under that ice. Shown here, you can see the rover rolling around on the underside of the ice, investigating sea algae that lives and thrives at that ice water interface. And what's really nice about our rover design is that it does not harm the biology or the chemistry at that interface, and it's very energetically efficient. When we get to a sample we want to investigate, we can stop the rover and just park it there for a while. Whereas a traditional submersible has thrusters, those thrusters disturb the interface, and those thrusters are also very energetically costly. And so you use up your batteries quite rapidly. And so this is a very novel design that leveraged rover designs on Mars. And so we were able to take some of our space advances and apply them to how to explore Earth's cryosphere. It's a rover that thinks the ground is up. And hopefully this video is playing. You can kind of see it roving along there. Is that video coming through okay, Joe?
It is. That looks fantastic.
Yeah, truly alien ocean on our home planet. And down in Antarctica and up in the Arctic, we have a lot to learn about what happens to this ecosystem as polar night begins. And so our goal is to someday have many of these vehicles deployed under the ice to watch the seasonal transformation in a way that, of course, we humans cannot. And there we are, pulling it out of the ice. So briefly, I'll finish by going to a dot in the middle of our ocean. This dot is showing you where the Mariana Trench is, the deepest trench in our ocean. It's 11 kilometers deep, about 7 miles down. And interestingly, when you do the math, the pressure in the Challenger Deep, the deepest spot in the Mariana Trench, the pressure is in the range of 110 or so megapascals. And it turns out that that is comparable to the pressures that we predict to be near the base of Europa's ocean. And so any of the robotic vehicles that we've sent down to the Challenger Deep, if you could magically transport them to Europa, they would do just fine. And so I was part of an expedition in 2012 that headed out to the Challenger Deep. This was an expedition led by James Cameron of Avatar and Titanic fame, a remarkable explorer and scientist in his own right. And so Jim, in collaboration with National Geographic and Rolex, built the Deep Sea Challenger shown here. And we were out there working hard to get this vehicle down to the Challenger Deep spot for the first time since 1960, when the Trieste made that dive. And that, of course, was a Navy effort. And this, of course, was a private exploration effort. Interestingly, since 2012, since Jim did this dive, Victor Vescovo and others have made many dives to the Challenger Deep. And so I think this expedition helped kind of reopen a new age of ocean exploration in the deepest trenches here on Earth. But as amazing as that dive in the human submersible was, we also had these robotic landers, these telephone booth size landers that were designed and largely built by Kevin Hardy, an amazing oceanographer and engineer. And these robotic vehicles, sort of simple as they were compared to the human submersible, we could leave them down at the bottom of the ocean and let them observe and wait around for biology for many, many hours, sometimes 12 hours, sometimes a full day. You can see the high-tech ballast in that middle image. Those are a bunch of weights that I think we might have stolen from a gym at the University of Guam. We don't quite remember where we got those. But here is a video of the true abyss in our own ocean. And what you're looking at here is a video captured of that robotic arm, that passive arm that just has a burn wire on it, and it drops to the sediments of the seafloor once the lander lands. And in this video, you can see that color bar. That is just to do some correction, and then a netted trap. And in that netted trap, you can see a fish head. And after several hours at the bottom, a few little critters came out of the abyss and started feeding on that fish head. And after a few hours, those few little critters turned into hundreds and then thousands of these creatures feeding on this fish head. And so here we are in the deepest, darkest depths of our ocean, and life is not just eking by, it's thriving. And whenever I show that, here's what that little critter looks like up close. It's an amphipod. That yellow is likely due to sulfur. It's the face only a mother could love. And whenever I show this picture, if there are any kids out there, inevitably I get a question of what do they taste like? Did anybody eat one? And sure enough, one of the engineers on the ship, after I was done dissecting one, he grabbed it and ate it. And after about 5 minutes, his stomach regretted that decision. And to put it politely, he returned that little amphipod from the ocean from whence it came. And so they don't taste good. But that information about the Challenger Deep with all those amphipods and that fish bait trap, as exciting as that was, it raised a whole bunch of new questions for us. And that being, well, how are those amphipods surviving when there's no baited trap for them to feed on? And that's where the second robotic lander drop really, I think, helps clarify our understanding of the geochemistry that makes biology possible in this deepest, darkest region. The second drop we did at the Sirena Deep. And what is astounding here, and if any of you geologists are out there, hopefully your jaws are dropping at this panorama of outcrop. Never before had rocks, a geologic outcrop, been seen at this depth. And that was exciting in its own right. But then when we serendipitously got some sediment samples back, some tiny little rock samples back, we're able to figure out that we think some of what we're seeing in these rocks is indicative of serpentinization. And that's kind of a very low temperature geochemical hydrothermal activity that generates things like hydrogen. And upon closer inspection, we saw that some of these rocks look like this. And here's where the biologists get really excited. These bearded rocks of the Sirena Deep within the Mariana Trench, we call them the bearded rocks for obvious reasons, and they look quite hairy. These filaments, we think, are microbial mats that are growing off of the products of serpentinization, very slow hydrothermal aqueous geochemistry percolating up through those rocks, allowing the microbes to make a living. And then those microbes are farmed by the amphipods. So a very exciting discovery that we published just last year. And here we are in the deepest, darkest, most extreme environment in our own ocean, where conditions are comparable to what we expect to find on Europa. And again, life is not just eking out a living, it's thriving. So I'll finish with my dream of dream missions. This is a mission that clearly my dog loves. It's a mission that I hope will take place within the next few decades. I've been working hard to help not just with Europa Clipper and the lander, but this melt probe mission would come after the lander and would involve a probe that has a heat source at the tip, perhaps nuclear or otherwise, and that probe would then melt through the ice shell, leaving behind a tether and some acoustic relays. Once it got to the ice water interface, it would release an autonomous underwater vehicle. We would then explore the ice water interface. We wouldn't be able to joystick this from Earth, so we'd have to have a bunch of AI and autonomy on board. And then hopefully it would be able to make its way down to hydrothermal vents on the seafloor of Europa. And in our dream of dreams, as depicted by Cameron and all of us in Aliens of the Deep, we then make contact not just with microbes, but also astoundingly beautiful jellyfish-like creatures. So that's the dream of dream missions. And I'll just finish by saying, by going back to one of my all-time favorite images, an image drawn by the hand of Galileo, an image from over 4 centuries ago, an image that revolutionized our understanding of physics. And this, of course, is that image of Jupiter with the 4 satellites around it. And as you appreciate, when Galileo first discovered these moons, he thought they were stars. He named them the stars of Medici because he wanted to keep his funding going. He was no idiot. He was getting paid by the Medici family. But as night after night, he was able to see that they do in fact go around Jupiter. He figured out that they are moons. And with that discovery, he helped put the final nail in the Aristotelian view of cosmology, the idea that the Earth is at the center of the universe. And he helped open the doorway to the Copernican revolution. And in the decades that would follow, with the work of Newton and others, we would come to appreciate that the laws of physics work beyond Earth. And then with the advent of spectroscopy and even better telescopes, we would come to appreciate that the laws of chemistry work beyond Earth. And then with the advent of the space age and sending spacecraft to the moon and Mercury and Mars, et cetera, we would come to appreciate that the principles of geology work beyond Earth. But when it comes to that 4th fundamental science, when it comes to the science of biology, the phenomenon of life, the phenomenon of what makes us us, we have yet to make that leap. And part of what excites me about the time in which we live is that, again, for the first time in the history of humanity, we can go out there and explore these distant alien oceans and potentially discover life on these far and distant worlds, and perhaps, maybe, see whether or not biology works beyond Earth and potentially bring the universe to life. Thank you so much. No, I ran a little bit over there, not too bad, but hopefully we have time for some questions.
I certainly appreciate the talk, Kevin. That's absolutely fantastic. And we had a lot of questions come in. So I'm hoping you're okay with a few of these. And what I would ask is a few of you had put several questions in, for sake of time and to respect Kevin's time. I was going to ask for those of you who did post several questions to ask perhaps the one question you were most curious about, and we'll just go through those in order. So Peggy Mueller. Peggy, are you there? Would you mind coming off of mute and asking your question?
Oh yeah, I am here. Very interesting book and great talk. And I love your analogies in the book. I really appreciate them. They really help me understand things. So I was reading an Astronomy Nature article that talked about impact. The name of it, I don't see my question now. It's called Impact Gardening. And they were saying that impact gardening likely churns the top 12 centimeters or so of the European ice. And that if that was the case, it would bring up, if there were microbes or anything down there, it would bring them up, and then they'd be exposed to the radiation of Jupiter and possibly turned into unrecognizable goo. So I wondered what you thought about that, and if you thought that was truly something we should be concerned about.
Yeah, so the a few different threads there, and I know that article well. A number of colleagues are on it, and it's a good article. There are some. It got a fair amount of press for some of its relevance to the lander. Importantly, the key aspect is that in areas where Europa has its youngest surfaces, it's not gardened to that same depth. And so what kind of went underappreciated in that article is that you just target the younger surfaces on Europa, and you don't have to go as deep to get pristine material. But more importantly, perhaps, is that we have never sampled pristine material either on Earth or on Mars or any of these other worlds. The idea that we're going to get pristine organics is flawed. On Mars, to get quote unquote pristine organics, we would need to drill a meter down just to get to a depth that that goes beyond the galactic cosmic ray radiation processing depth that occurs over the billions of years of geologic history on Mars. Now, again, there are some caveats to that, but the key thing being that for the Europa Lander, we would target young surfaces. And while radiation might modify absolutely pristine material like a strand of DNA, what we've learned from ancient rocks on Earth is that there are stages of modification, and you can still tease out various biosignatures even with irradiation having modified them. And coupled with that, there's structural radiation biosignatures that are structural biosignatures that are not modified by radiation. And lastly, I'll just say that the robotic arm on the lander can sample quite a bit deeper than just 10 centimeters. So we're robust to being able to go deeper than the radiation processing depth.
Okay, thank you.
Sure, great question.
All right, Bill Spitzeri, you had a question, and I think may have been answered in one of the last animations that Kevin showed us.
Yes, thank you. Yeah, I just mentioned that somebody from JPL, possibly you, sir, was speaking 4 years ago. I think it might have been at Casper, Wyoming, at the solar eclipse meetings that were up there. Maybe it wasn't you, but they talked about the mission that you melt a hole in the ice that you showed in the video. And I was just wondering if, and you seem to have answered that, if that was seriously being considered at this point. You did mention that the mission, isn't, like fully funded yet, or whatever the term was that you used.
Yeah, that's right. So the lander itself isn't even approved, and it's been a Sisyphean task of trying to keep it alive. It does matter a lot having public support for these missions, and so if you want to see us land on Europa and eventually melt through, you all as a cohesive astronomical society, I encourage you to contact your Congress people, et cetera, and express your support for these kinds of missions. In Houston, actually, John Culberson was a tremendously strong supporter of NASA broadly and Europa more specifically.
Member of our club, by the way.
I meant to send him an email and say I'm doing a talk, but as Joe knows, I just barely made it out here because I was on a drive. But in any case, I sure hope we can get approval for moving forward with the lander. And once we've got lander moving forward, then a melt probe would utilize the data returned from the surface to help us better design that melt probe and tell us exactly how long of a tether we need, how deep the ice shell is, how thick the ice shell is, and how deep the ocean is. So yeah, I'm going to keep on working hard on this stuff and hope that the public and my fellow scientists will continue to be excited by it.
We'll certainly
Thank you for your work.
as well.
Well, thank you for taking an interest in.
Thank you.
And NASA's a taxpayer agency, and so you all are shareholders in what we do.
All right, Don Selly had a few questions. Don, did you want to ask one in particular?
Yeah, because I think the first one got answered in terms of the goo on the surface. You know, we have to get that. I got that one done. I actually designed ROV systems in the mid '90s. Okay, so the thing that two things: reliability and communications, right?
Yeah.
And when I look at the melt probe, I know tether technology has come a long way. Okay. But I can tell you the biggest problems we always had were with tethers. I imagine you probably already know that. Is there any thought been given to any other technology? For example, we do use seismometers on Mars now, right?
Yep.
And at one point in time, I know there was like a Navy program that used low frequency radio waves. But I'm also thinking, is it possible to do low frequency sound waves and get them on the surface? Just a thought.
Yeah, it's a great thought, Don. And yeah, I remember in some of our emails talking about your past history with ROVs and stuff, which is fantastic. And it goes to exactly what I was saying before, which is like, you know, we're a long way off from figuring out how exactly to do a melt probe on Europa. And in order to do that, we need to make these technologies that we use here on Earth much more robust, because it's only through testing and improving those capabilities that we will someday be able to have the confidence that these things will work on these far and distant worlds. And so, like you're saying, the tethers, you know, just as one example, the Buoyant Rover that I showed you down in Antarctica, we can operate that untethered. And in our earliest incarnation of it, we had a UHF transmitter that touched the ice. And so the signal was able to go through about 2 meters worth of ice up in Alaska. And then it was relayed up to the Iridium network, and we were able to operate buoy from JPL. Now, of course, that was a very small scale with transmitting through ice and not through liquid water. And then in Antarctica, we went back to a tethered system just because we wanted to make sure that if anything went wrong with the Buoyant Rover, we could use that tether as a mechanical tether and pull it back out the hole in the ice. And sure enough, on the last day, that tether got wound all around the wheel, and it was a mess. And so by the time, you know, it looked like we looked like a bunch of stupid fishermen. We were, you know, caught a lure in our fishing line. So yeah, we got a long ways to go, and thankfully, there's a lot of great work to do here on Earth as we work to advance those capabilities.
Yep, and I will say, just from the time I was doing the ROV design and the autonomous vehicles now that are actually being used commercially, I think there's lots of reason to believe that technology is going to continue to really progress. So
yeah, and I'm working very hard with a number of colleagues. So I've got I'm a what the formal language is, but basically I have an appointment at Woods Hole Oceanographic Institution in Cape Cod, and part of the rationale for that is that we've got a team at JPL and a team at Woods Hole designing kind of next generation ROVs with a mind towards utilizing CubeSat technologies in the ocean.
I appreciate it, and keep it up, because it's going to help the commercial side and ocean exploration as well. I think it's really phenomenal. Thank you.
It's a win-win. Oh, thank you.
All right, and unfortunately, we have more questions than I think we have time for. But I was going to see if you had if 2 more questions were okay.
Oh, absolutely. Yeah, sure.
Okay. Don Borg Anderson had several questions. Don, did you want to ask one in particular?
Yeah, what I'm going to do is try to combine both of them, to be honest. My first was more or less just a statement. Being that we're carbon-based life forms, and we tend to, by default setting, look for what is like us as far as how we define life. I know in the past there's been talk about silicone-based life. Now, with that being said, I'm going to mention part of the second question too. Is artificial intelligence going to possibly help in presenting different theories of what could predict other forms of life that are quite different from us and what we know of life?
Yeah, that's a great question. And I'm sorry, what's your name again? I
Dawn.
missed-
Just
Dawn. Yeah, so it's a great question, Dawn. Both of them are great questions. Let me go to the second one first. With respect to artificial intelligence, where that really will come into play is with machine learning algorithms that can explore an incredible diversity of space in silico, in the coding world of simulated molecular evolution,
Right.
to see how the origin of life itself might have arisen. There are a number of labs around the world, and I do a little bit of this in my lab, where we're trying to understand the chemistry of the origin of life. And in an ideal scenario, or perhaps ideal, maybe not ideal, some of these labs would be able to cook something up and show a viable pathway for the origin of life. The reality is that there's a lot of permutations to get done in a lab, and not much time for grad students earning PhDs to get those experiments done. Meanwhile, AI and machine learning algorithms are getting better and better. Our algorithms for simulating chemistry are getting better and better. And so I think AI could help solve the origin of life question and then help inform experiments. Now, when it comes to completely different forms of life, like you were saying, when we think about alien oceans, we're largely focused on carbon and water-based life. That's for good reason. We can test that hypothesis. We formulate the hypothesis of what makes life on Earth work, and we can then extend that to worlds like Europa. We really can't, since we don't have an example of it, formulate a really viable hypothesis for non-carbon-based life. But what we can do is try and make sure that our instruments and our design and the design of our experiments that are looking primarily for water and carbon-based life are broad enough that if there is life unlike life as we know it, we won't miss it. And so many of our missions are designed with payloads that are driven by, let's call it 80% hypothesis testing capabilities. And then 20%, maybe it's 30%, maybe it's 40%, depending on the mission. Some fraction of discovery-driven science. So, make sure you've formulated your science questions very well, and your payload, your instruments can address that. But then also make sure that payload is open enough to discover the unexpected. And Titan may be a great example of that. When we get there with Dragonfly, Titan's got these methane lakes, and who knows, maybe in the solvent of liquid methane and ethane, some bizarre form of life has taken place. It'd still be carbon-based, but it would use methane as the solvent, not liquid water.
And any further research on the silicon theory of life, or adding to that?
Nothing that I've seen recently. I go through a bit of that in my book. There's a chapter on the periodic table of life, and oh goodness, I'm blanking on my colleague's name. Oh, goodness, he's at he started an institute down in Florida, and he's done a lot of great work on alternative biochemistries. So in any case, that's a shameless plug for that chapter of my book on the periodic table of life.
Well, thank you very much. That's a great answer, and I really appreciate your time in explaining that all to me.
Thank you for coming tonight.
All right. And again, I apologize, folks. There are more questions than we have time for, but we'll get to the last question and then kind of a comment after that. Well, maybe it's a question, but Hai Wen was had a question about the data from the Europa Clipper mission. Hai, do you want to come off mute and ask?
Sure. Thanks, Joe. Hey, thank you very much for taking the time out and giving me this great talk.
Thank you. Hi, Wen. Is that?
Yes, it's hi. It's like hello. Europa. I've been a great fan of Europa Mission because I had a tiny involvement with the original Europa orbiter a long time ago, and I still have a couple of colleagues that are working on the Clipper mission currently. So it's great. So question I have is, do you have any instruments on board that on the Clipper that would help detect any sign of biological life? And are there any data on the vehicle that would help you push the lander mission up on the priority queue and get that funded sooner rather than later?
Yeah, it's a great question. Hi. So the answer is yes. There are a number of instruments. The one that I'm most directly involved with is the kind of next generation of the cosmic dust analyzer that I talked about with respect to Cassini, and it's called SUDA. And so with the DNA standing for dust analyzer. And if Europa has plumes erupting out of its surface, which we think it may well have, the Hubble Space Telescope has detected some hints of plumes. I've been on a couple of teams that have published on that. And so the Clipper mission will be able to fly through any Europa plumes and taste some of that material. And the SUDA instrument is a mass spectrometer, and then there's another instrument called mass specs, which is kind of like the next generation ion and neutral mass spectrometer that was on Cassini. And both of those instruments will be able to detect organics. They're very complementary in that they are able to analyze gas phase material versus grains, shorter, smaller organics versus larger organics. And so, and possibly even detecting things like amino acids. Now, I sure hope that we can move forward with the lander before Clipper gets out there. And the reason for that is manifold, but just to highlight a couple of things. It's going to take approximately 14 years from the time we get the green light to move forward with the lander to landing on the surface. And so if we wait until Clipper is out there collecting data in, say, 2030, and we get the green light, that means that we're not landing on the surface until the mid-2040s. Now, that may just be the harsh reality of solar system exploration, but what it also means is that we're not going to be able to use Clipper reconnaissance imagery or Clipper as a comm relay asset as part of the lander mission. Now, the lander currently does not have Clipper comm relay baseline, but in theory, if we got out there and the Clipper mission was still functioning, and for that matter, the JUICE mission was still functioning, well, maybe we might be able to pipe some data down through those spacecraft. But more importantly is that we're going to be dependent on the Clipper imagery for doing landing site selection. And we don't want that imagery to go out of date. Let's imagine we want to land next to a plume on Europa. Well, we better land in sort of close cadence to when that image was collected, when that imagery was collected, as opposed to getting there some 15 years later and having that carry a whole new spacecraft and redo that reconnaissance, spend the billions of dollars to add an orbiter to the mission, et cetera. But rather, having the lander go and land a few years after Clipper is done with its prime mission, well, then that recon data will still be hot off the press to some extent and viable for safe landing site selection. Does that make sense?
Yeah, I didn't even think about the fact that the ice surface will be changing in that time between you launch the lander mission and when you get there. It is, but 14 years, that's a number I haven't heard of before. Yeah. But thank you very much.
Yeah, thanks for your question. And thanks to all of you for attending, for buying the book, right? I don't know if any of you have written reviews, but reviews go a long way these days. Just given that everything is remote and all that. So greatly appreciate that. And it's been a pleasure talking with you all.
Yeah, absolutely. And I know Marjorie, I think she may have dropped. She did ask a question about unidentified submersible objects and things like that. And I'm sure you get a lot of questions about UFOs, USOs, and things like that. But we wanted to stay focused on the work that you're doing here. And the last question by Sanjay Pandey, do you want to come off mute and ask? I think it's a good one to close on.
Yeah, sure. So my question was, I'll be interested in getting a copy of the book, but I was also looking to see if you can personally sign it. And how do we go about getting a signed copy from you?
That is a great question. And sadly, I was scheduled to give a National Geographic Live presentation in Houston last year. And I had several talks lined up, and then of course they were all canceled due to COVID. But that was going to be the time to do exactly the book signing type of thing. It's difficult for me to do sort of the mailing and so on and so forth. But let me think about that. Maybe I'll follow up with Don and Joe, and if there is like a batch of books perhaps that the Houston Astronomical Society, the crew would like signed. I don't know if it makes sense, Joe, to coordinate with you on sending them out here or something like that. Or
yeah, certainly.
I know Princeton University Press arranged for that someplace else, but yeah, I wish I could just go through the computer and
yeah, we've done similar things in the past, so yeah, we can certainly talk offline and see how we could get a large shipment sent over to you and take care of the shipping back. So yeah,
you can send a spacecraft to Europa. We can certainly send a book. Come on.
Hopefully we'll figure something out.
Exactly.
I did see some other people express similar interest in the chat box, so there are more than just me wanting a signed copy.
Okay.
Yeah, we can reach out to folks after this and just see what we can do for a group buy, and then Kevin, if it's okay with you, coordinate with you on the back end.
Yeah, that sounds perfect.
Perfect. All right. Well, Kevin, how can we keep up with all the other things that you're doing? Are you on social media or anything like that? I
am, but somewhat horribly so. I need to be better. I'm at Alien Oceans on Twitter, and then on Instagram I think it's just my Kevin_Peter_hand, and I really should get better about that stuff. I come to it kicking and screaming because like longer form. That's why I wrote a book. Right. Longer form expression of ideas. But yeah, I guess short of anything else, Twitter and Instagram are the best ways to keep in touch. And I am working, so I'm a staff scientist on the Mars 2020 mission. I'm one of 2 campaign science leads, and we just drilled on Mars. I can't really talk too much about what's going on there. I don't know what's been released to the public so far, but I'll try and retweet some of that stuff. It's, as much as I've talked about Alien Oceans, being a part of the Mars 2020 mission has just been extraordinary. And the geology that we're seeing directly in front of us and that we're going to be seeing throughout that mission is just astonishing. We're literally in an ancient lake bed. Wow. If there's any place to search for ancient signs of life on Mars, it's this landing site. Absolutely. Well, we're really excited about you. It looks like you're in the middle of a lot of the research that's being done there. And I saved my question, I figured I wouldn't ask it, but we had Dr. Justin Filiberto from the Lunar and Planetary Institute on with us several months back. And
This was right before the announcement of phosphenes in the atmosphere of Venus as well. And we're starting to see others come back and say, yeah, that's probably something else. But I was going to ask you about that, but that's, we'll get to that some other time. But again, thank you for joining us today. This was an absolutely fantastic talk. And for those of you who haven't purchased the book, we will arrange for something, if you want a signed copy of the book, to hopefully get that signed by Kevin. And if you don't want a signed copy, you can always go out to Amazon and other book vendors and just pick up a copy there as well. So Kevin, thanks again for joining us. It was a wonderful presentation.
Thank you so much. It was a real delight to be with you virtually all.